RL circuits are circuits that have both a resistor and an inductor. And in a lot of ways, their behavior is similar to the way RC circuits behave, or maybe analogous would be a better way of saying it. So for an RL circuit, we have a battery, we have an inductor, which, it has a coil in it, or a solenoid, which we just indicate in the diagram by making this little sort of curlicue thing. And then it has a resistor. And generally you put the switch up here, but it doesn't really matter. And there's the switch. Okay. So when the switch is closed, we already talked about how an inductor behaves and how this inductor will impede the current. So what that means is that it takes longer for the current to build up, but eventually that current kind of overcomes the inductance, and we get that a current that is equal to the EMF of the battery over the resistance of the inductor. And this is our EMF, and this is L, inductor. So eventually, the inductor acts like a wire, but initially it does impede the current. And the way that the current builds up is the equation looks a lot like the equation for the charge building up on a capacitor in an RC circuit. In the case of an RL circuit, we still have a tau, which is the characteristic time of the circuit, but instead of being RC, it's L over R. And then the current, as a function of time for an RL circuit, is the EMF of the battery over R times 1 minus e to the minus t over tau. And this, like I said, this looks a lot like the equation for the charge on a capacitor as a function of time in an RC circuit. And we can solve different kinds of problems with this. For example, let's say that we have the following situation. 12-volt battery, 56 millihenry inductor, and two 15-ohm resistors in parallel with each other are in a circuit here. I want to know what is the current one-time constant after the switch is closed, when does the current reach half its maximum value, and what is the current a long time after the switch is closed. So first off, let's consider what's happening. We have here an RL circuit, but instead of just one resistor, this is an equivalent resistance. And my camera decided to turn itself off. Anyway, so we have these two 15-ohm resistors, and they are in parallel with one another. So we know we can find the equivalent resistance by adding reciprocals. So 1 over R plus 1 over R is 2 over R, so the equivalent resistance becomes R over 2. And in this case, R over 2, 15 over 2, you get an equivalent resistance of 7.5 ohms. So then what is the current one-time constant after the switch is closed? Well, this means we're looking at when t equals tau. And when t equals tau, we have the current, I of tau, equals EMF of the battery, 12, over the resistance of the resistor, which is the equivalent resistance of 7.5, 1 minus e to the minus tau over tau. That's the negative first. So that current, not as a function of time, the current at that time comes out to 1.011, etc., or about 1.0 amps. Okay. When does the current reach half its maximum value? Well, the maximum value of the current is the EMF of the battery divided by the resistance, E over R. So when does the current reach half its maximum value? Well, this is its maximum value, so the time it reaches half is when the current divided by this equals 1/2. So we can say 1/2 equals 1 minus e to the minus t over tau. And tau is L over R, so that's 56 times 10 to the minus third over our resistance, which is 7.5 ohms. And if I throw all that into my calculator, I get that t equals 0.005175, etc., or about 5.2 milliseconds. 3 decimal places, 5.2 milliseconds. What is the current a long time after the switch is closed? Well, a long time after the switch is closed, the current is just what it would be if there was no inductor. And so a long time after the switch is closed, that current is just the EMF of the battery over equivalent resistance, which is 12 over 7.5, which I can punch in and get 1.6 amps. All right. So that's how RL circuits work, and I think you can see, without me belaboring the point too much, how they're very similar to the way that RC circuits operate. Now, because this inductor resists a change in current, there's work that the battery has to do to get that current going, and that work, causes a change in energy. That energy doesn't just disappear. That energy is actually stored in the magnetic field of the inductor. Now, we know from before the other day that the EMF of the battery is equal to that inductance times, it's actually a di by dt, but we can say delta I over t. And so if we close the switch, and so that our initial current is 0, we can say that the EMF is equal to Li minus 0 over t. All right, and so the average current is going to be half this value because the current's building up from 0 to this I value of the current. So our average is just going to be half that current. So that means that the average power of the circuit, and power we know is IV. Well, the voltage is always the same, and the V is just the EMF of the battery. And so we can say that the average power is 1/2 I times Li over T, which is half Li squared over T, and power times time, that's just work, because this power is work per time. And so then the work done by the battery, which is equal to the energy stored in the inductor, is equal to 1/2 Li squared. So this is the energy stored in the magnetic field of an inductor. If you remember from back when we were talking about capacitors, maybe I should say U, inductor, and this is a magnetic energy. The energy stored in the electric field of a capacitor was half CV squared. So we continue to see this parallel between, not to be confused with resistors or capacitors in parallel, but there's this analog, I guess you could say, between inductors and capacitors and the way they function in relation to the magnetic field, or the way an inductor functions in relation to a magnetic field, to the way the capacitor functions in terms of the electric field. Okay. Now, for a solenoid, which is a particular kind of inductor, for a solenoid, the inductance we worked out last time is mu naught, not m, n squared times the cross-sectional area times length. Okay? So, if we plug that in, the energy becomes 1/2 times mu naught n squared a l times I squared. Okay, well, that doesn't look all that helpful, but if we recall that the B field of a solenoid, well, you may not recall, but the B field of a solenoid is mu naught n I, so we can write this as the B field squared, which would be mu naught squared n squared I squared. So the n squared I squared happens, but this is just mu naught, which means we have to have a mu naught in our denominator, and then the half, and then we have area times length. And the cross-sectional area times length is just volume. So the magnetic energy density simplifies very nicely, just like our electric field density did. And we call that little u sub b, that's equal to the B field squared. This is a volume, so this is magnetic energy density is the energy per volume. I'm going to say VOL, not so we don't get it confused with V for voltage. Is just B squared over 2 mu naught. Recall electric energy density was epsilon naught E squared over 1/2 epsilon naught E squared. So the only difference between these two is that B and the E are there, and then the mu naught goes in the denominator versus the epsilon naught going in the numerator. So they're very related, and like it was for the electric field, this, though it was derived for an inductor, this relationship, this energy density relationship, is true for all magnetic fields. So that is the energy stored in any magnetic field. So let's do a sample problem here. So here's our problem. We have a circuit, a 36-volt battery, a resistor of 92.5 ohms in series with an unknown resistor, and an inductor, 75 millihenries, 3.11 times 10 to the minus third joules of energy stored a long time after the switch is closed. We want to find R. Okay. Well, this is a problem that we can solve using the principles that we've learned about already. We know that the energy stored in our inductor is equal to 1/2 Li squared, and so that will allow us to find the current because we know the inductance of the inductor, and we know the energy stored in the inductor. And then we can say from our relationship of RL circuits, we know that the current a long time after the switch is closed is just the EMF of the battery over that equivalent resistance. And so we know that I equals EMF over REQ, which is the EMF, over the sum of those two resistors because they are in series. So we can say that our energy stored is 1/2 L E squared. Actually, let's just leave that as E over REQ squared. And we can start, we can rearrange this a little bit. So we've got square root 2U over L would equal E over REQ. We could take a reciprocal, and so you'd have root L over 2U, be REQ over E, so times E, and then we can subtract off that known resistance because our REQ would be the unknown resistance plus the known resistance. And if we punch in numbers, that gives us, let's see, 36. Square root L is 75 times 10 to the minus third over 2 times the energy stored, 3.11 times 10 to the minus third. 10 to the minus thirds go away. And then we can subtract off that resistor that we know, 92.5 ohms. And if I punch that into my calculator, I get that resistance equals 32.5080, etc., which is approximately 33 ohms.